This is slide number 21 and I am your presenter Asloob Mudassar. Last time we have defined the integral, that is the Fourier integral we have defined earlier. Now we are examining the conditions that the integral must satisfy. You know that the integral we have defined earlier, which is we called it as a Fourier integral, has two integrand limits. One is going from minus infinity to plus infinity on both integrals for a two-dimensional case. Now we impose two mathematical conditions for the existence of such such integrals. One is that the integral should exist within the limits where the function o of x and y exist and defined. So the integral should exist within the limits where the function o of xy is defined. This is the first condition. The second condition is that o of xy may have a finite number of discontinuities within the limits but no infinite discontinuity. So there should not o should not have any infinite discontinuity, because the integral could not exist at such a discontinuity. However, the function of xy may have a finite number of discontinuities for which the integral could be solved. So the overall we can precisely say that in the both conditions means that the integral should exist for the function for the function o, which is a function of x and y. So the integral should exist for this function. Some special objects that do not satisfy the mathematical constraints given above, but still their optical Fourier transform exists. So these two definitions we have given in paragraph number 1. These two conditions sometimes do not exist for some objects, but we have noticed that we shall notice that their optical Fourier transform still exist, and we shall examine them, what kind of those objects are. The three examples, there are three examples of such objects are presented here. They are, what are the examples? Number 1 is a point source. Number 2, a plane wavefront of infinite extent. The number 3 is a sinusoidal grating of infinite extent. These three are the special objects for which the Fourier transform does not satisfy the conditions, but you see that their Fourier transform still exists. And these three objects are given here. On the left hand we have a point source embedded in an opaque region. So the light cannot pass through the opaque region, but there is a point source at the origin and giving an intense light over there. And it is defined mathematically. It is an object which we have referred to as the object O1, and it is defined by the delta function, delta of xy. And you know that delta of xy means that when x and y are both 0, then we shall get an impulse over there at the origin. But if x and y deviates from the 0, we get immediately 0 response. And you know that delta functions have many definitions in mathematics, and we are considering only over one definition, that is the delta function is equal to the limit when n goes to infinity on two functions. One function is n square, the other function is e to the power minus n square pi into within the brackets x square plus y square. So we shall examine this function in greater detail in the next slide. The second function in the middle is a plane wave. The arrow shows that the plane wave has infinite extent in all directions, and this is we have named it as O2 function, and O2 function is equal to 1. We have dropped over here the constant phase factor, because the constant phase factor with the plane wave would not change the physics. So O2 of xy is equal to 1. It is a plane wave of unit amplitude of infinite extent. And the third object on the right is a sinusoidal function. You see that again the arrows shows that this sinusoidal function has infinite extent, and it is defined mathematically by 1 plus cos of 2 pi fx, and we have regarded this as the function O3. And you know that this is a single frequency f. So we have this object. For these three objects we shall see that the Fourier transform definition would fail as given in the previous slide, but still their Fourier transform exists, but optically. Let's consider the definition of the ideal delta function that we have given. So O1 was defined by the delta function, delta of xy, and its mathematical definition in terms of the two function n square multiplied by the exponential function e to the power minus n square pi within the brackets x square plus y square, and the limit is n goes to infinity. Now you know that this definition, I have explained that this definition is consistent with the definition of the delta function. The definition of the delta function is that when both x and y is 0, then this function will blow up. That is, we get a impulse there. But when x and y both any one of them is non-zero, then of course the delta function is will be 0 immediately. And we would see in the following two statements that the definition of this that is n square multiplied by e to the power minus n square pi into x square plus y square also give us the same definition as we understand from the definition of the Dirac delta function. So let's read the statements. The exponential function is dominant over the squared function when x and y deviates from 0. So when x and y are both non-zero, or at least one of them is non-zero, we would see that the exponential function will dominate the n squared function, and so immediately it would fall to 0. The second function n square dominates the exponential function and rises to infinity at the origin. So when x and y are both 0, what will happen? E to the power exponential e to the power becomes equal to 0, which is 1, and n square then dominates. So at the origin, when x is equal to 0, y is equal to, the exponential function contributes 1, but the n square function goes to infinity immediately. So this function actually gives us the same definition as we expect from the Dirac delta function. So physical point source is not infinite at its location, but you know that our physical point source will not be infinite in the sense that we have defined mathematically, but still it will have a very large value at the point source. So this is the end of presentation slide number 21.